Today I will discuss the possibility of generation of electromagnetic waves by electron beams. The device that employs a slow wave is called Cerenkov free electron laser. This is an electromagnetic wave which is slower than which moves slower than the electromagnetic wave in free space, and an electron beam can generate this wave. The device is quite interesting. I will discuss a simplest structure that can slow down a wave, and then I will discuss the interaction of an electron beam to a transverse magnetic mode of this guiding structure. We will reduce the dispersion relation, obtain the growth rate, and discuss the saturation of this instability. Well, this is the reference. Well, electromagnetic waves are a little difficult to handle, to be excited by electron beam. The reason is that if the beam is traveling, suppose in this direction, and it sees an electromagnetic wave, so this is my electron beam, and if my electromagnetic wave also travels in the same direction in free space, then this electromagnetic wave will have a transverse electric field. So, first of all, there is no longitudinal component of this electric field of this wave, and hence there is no direct retardation of this electron beam, and hence this scheme is not working. This wave cannot extract energy from the electron beam. Second problem is the Cherenkov resonance. For momentum and energy conservation, we found that if the wave is of frequency omega and of wave number k, then momentum and energy conservation, if the electron has to emit a photon of frequency omega and wave number k, then this condition must be satisfied. This is known as the Cherenkov resonance condition. Only when this is satisfied, the momentum and energy are conserved between the electron and the photon. Because in free space k is omega by c. So, if I divide this equation by k, magnitude of k, this becomes omega by k has to be equal to k vector upon k magnitude into V0b. So, if there is an angle theta between k and V0b, then this becomes V0b cos theta. Because V0b is less than c, cos theta is also less than c. So, this is the angle, suppose this is my k and this is my beam velocity. So, if the angle between the two is theta, then this condition cannot be satisfied in free space, because omega by k is c. So, there are two problems. One, you require a component of the electromagnetic wave in the direction, electric field of this wave in the direction of beam propagation, and secondly, you want to slow down the wave. A wave can be slowed down if you pass this wave through a waveguide. Suppose this is a waveguide. If it is having vacuum in the interior, then the phase velocity of the waves guided by a waveguide are always bigger than c. So, this condition cannot be satisfied. However, if you line the waveguide by dielectric, suppose you fill a dielectric here in this region, near the walls fill a dielectric, this is a dielectric here, load a dielectric here, then there is a possibility that the electromagnetic wave that travels through this structure can have a velocity, phase velocity less than c, and this condition can be satisfied. This is what is really happening in a device called Cherenkov free electron laser. You slow down the wave by putting a dielectric lining, this is dielectric lining here, near the walls. So the effective velocity of the wave in this region becomes less than c, and then this such a structure, guided structure, supports a special kind of wave called TM mode, and those modes have a finite electric field in this direction called EZ. If this is the direction z axis, then transverse magnetic mode has a component of wave electric field in the direction of axis or along the axis of the waveguide, and that can retard the beam electrons and convert their energy into electromagnetic energy. This is what happens in a Cerenkov free electron laser. There is another interesting device that does not slow down the wave, but it says that I want to generate an electromagnetic wave going in this direction with a transverse electric field, and the electron beam is coming from here like this. There is a possibility of energy transfer from here to here if there is a magnetic field in the system which can take momentum. So if you can have a structure like this with alternate polarity, suppose you put a magnet here that produces a magnetic field in the vertically upward direction, and another set of magnets which produces a magnetic field in the downward direction. So if you have this kind of a static magnetic field configuration, which is called a wiggler, and if wiggler is of this form, some amplitude and exponential of I kwz. This is your electromagnetic wave which will have an electric field of A exponential minus I omega t minus kz. So this is electromagnetic wave that you want to excite by the beam, and this is in the presence of a magnetic field called wiggler magnetic field. What does this do? If the electron sees this electromagnetic wave, the electron will oscillate in the direction of the electric field of the wave. Well, rather than I have not done this properly. These two are chosen perpendicular to each other. So rather than I will choose that this electric field is really in this direction, perpendicular to the plane of the paper. So if this electromagnetic wave makes the electron oscillate in this direction, then those electrons will experience a Lorentz force due to this magnetic field, and that will be in this direction. So this is the Lorentz force. Due to the V cross B interaction of the electrons which are oscillating due to one velocity and the magnetic field due to the wiggler. So this force is in the same direction as the direction of electron beam propagation. So Lorentz force which is a product of minus E, the electron charge, and electron velocity and magnetic field. So this force is parallel to z axis, and if I multiply Vw here and with this velocity due to this, then this force has a variation, multiply these two exponents of the form exponential minus I omega t minus k plus kw into z. So the force now does not have a phase velocity omega by k. The phase velocity of this force is omega upon k plus kw. So this force has a velocity k plus kw, and whenever this is equal to beam velocity, a resonant excitation of this wave can take place. So you have not slowed down the wave, you have not introduced any longitudinal component in the electric field of the wave, but just by sheer presence of a magnetic field, you can create a force on the electrons due to the mutual interaction of the electromagnetic wave and the wiggler magnetic field, this force whose frequency is the same as the frequency of the wave, but wave number is a sum of the wave number of the wave plus that of the Wiggler, and phase matching condition then becomes this much, and such a device is called free electron laser or FEL, free electron laser. We shall discuss in substantial detail the mechanism of a free electron laser, but today I would like to focus my attention on the previous device that I call as Cerenkov free electron laser. If the device employs a non-relativistic electron beam and a different kind of a structure is also known as traveling wave tube. Traveling wave tube. But I will be focusing my attention on Cerenkov FEL. TWT treatment is very similar. Now, in order to simplify the mathematics, I want to really highlight the physics of this process. So, I will, rather than considering the dielectric to be confined near the boundary as if the effective permittivity medium is filled in the entire region. So, I will presume that this dielectric of effective permittivity epsilon r is filling in the waveguide. This is, I will take as z axis, and the radius of the waveguide I will choose as a, and I will be considering the excitation of a TM mode of the waveguide. TM mode is the mode which has a component of electric field in the z direction also. So, electron beam will be launched into this device, and we would like to see how the wave amplitude grows in this structure. A schematic of a Cerenkov FEL is like this. You have a gun that produces an electron beam, then you have a interaction chamber, this region, in which you have a dielectric lining or slow wave structure, and in order to guide the electron beam, you put a, usually you put a field coil here that has a winding wrapping around the plasma, this chamber, and that produces an axial magnetic field. So, this is written like this. There is no plasma here, simply electron beam is traveling, and so there is a guide magnetic field in this direction, and after the beam emerges out of this structure, the beam is taken to somewhere here called beam dump. This is called a spent beam. The initial beam is launched here, this is called gun or beam source, and beam dump is there. I am focusing my attention on the interaction of an electromagnetic wave with this electron beam, and see how this wave is amplified, is excited. Well, the physics of energy transfer is very similar to true stream instability, that you need the electrons to be bunched in in retarding phases, and they must give net energy to the wave. Well, what is the equation of motion for this case? The same equation as I had written, dp by dt is equal to the electric force and the magnetic force. There are two magnetic fields in the system, the magnetic field of the wave, and there is a magnetic field that you have externally applied, DC magnetic field. So, E V cross B S, static magnetic field that I have applied in the z direction. to make mathematics simpler, I will presume that this guide magnetic field that I have applied is so strong that it does not allow, because Bs I have chosen to be parallel to z axis and I chose this to be very large, it does not allow the electron to travel perpendicular to the lines of force. So, this magnetic field confines electron motion along z only. So, I do not have to worry about the x component of momentum or y component of momentum, just consider this z component of the equation of motion. And how about this B field here? B field of the wave I can recover from the electric field of the electromagnetic wave, because from third Maxwell equation curl of E is equal to minus delta B by delta T. If I take my fields to be of this form, which is some function of r exponential minus I omega t minus k z z. So, I am presuming my wave to be traveling in the z direction with some phase variation like this, but the amplitude may not be uniform inside the waveguide, it may depend on r. It may also depend on the azimuthal angle phi, but I consider only the azimuthally symmetric mode. So, I ignore the phi dependence. If you have an electric field of this sort, then magnetic field will also have a same t and z dependence, and you can replace delta delta t by minus I omega. So, it becomes I omega b. So, if you know E, B can be written. My issue is to obtain the response of beam electrons to this electromagnetic wave with electric field E and magnetic field B. First of all, let me linearize this equation. Let me say that equilibrium is like this. There is no plasma, only beam electrons are there. So, the equilibrium has beam density is equal to n0 and beam velocity is equal to v0 in the z direction. This is my beam. Perturbation, and obviously there is a static magnetic field also in the equilibrium. There is no other field. Bs z, this is the magnetic field in equilibrium. Now I perturb the equilibrium. So, perturbation I will write electric field of the wave certainly will have many components Er, Ez, E phi, but they are all expressible in terms of the longitudinal components. So, let me write Ez is equal to some amplitude A which depends on R exponential minus I omega t minus k z. This is my Tm mode. Means Hz is 0, but other components of magnetic field are finite. In presence of this, I will have density is equal to n0 plus n1. The velocity will be v0 z plus v1 z, because magnetic field does not permit, I am presuming that any velocity of electrons perpendicular to z axis. So, this is the velocity. Let me linearize the equation of motion, treating electric field to be a perturbation, N1 to be a perturbation, V1 to be a perturbation, and magnetic field of the wave also to be a perturbation. So, then my equation of motion would become delta delta t of P, which is m gamma v, this is the momentum, plus v dot del gamma m v, this is again momentum here, is equal to the electric force, which is minus E minus E v cross B static minus E v cross B of the wave. First of all, examine this term. I am writing only z component. Z component of this term is 0 because Vs is in the z direction. So, this force will be perpendicular to z axis. So, z component is 0. How about this one? If I write V equal to V0 plus V1 and ignore the product of V1 with B because this is a perturbed quantity, then V0 is also in the z direction. So, this force will be perpendicular to z axis. So, this will give you V0 cross B, and this is the z direction. So, it has no z component. So, z component equal to 0 here. So, this does not give you a z component, this also does not give you a z component. So, this is the only place where z component will be there. So, when I write down here and divide this equation by mass, which is the rest mass, gamma is the Lorentz factor, V is the electron velocity. So, I think in order to simplify these terms here, I need to find the product of gamma V. Let us see what is gamma. Gamma as before is 1 minus velocity square by c square to the power minus half. So, when I write velocity is equal to V0 plus V1 all in z direction, then this becomes equal to, if you just substitute and carry out a binomial expansion, it becomes equal to gamma 0 plus gamma 0 cube into V0 V1 by c square, where gamma 0 I have written as 1 minus V0 square by c square to the power minus half. Just the way we had done this for two stream instability, we can carry out this expansion of gamma. Then linearize this equation. What we get? Gamma V turns out to be having actually only z component I am interested. So, this becomes gamma 0 V0 plus there is a term called gamma 0 cube V0 V1 upon c square into V0 from here. This is the one thing, plus gamma 0 into V1, and when you combine these terms, it becomes is equal to z gamma 0 V0 plus gamma 0 cube V1. Use this in the equation of motion and linearize, you will get delta delta t of V1 plus V0 delta delta Z of V1 is equal to minus Ez upon m gamma 0 cube. This is the linearized equation of motion including relativistic effect. It comes through gamma 0 cube. Now replace delta delta t by minus I omega, because the response should have same t and z dependence as the source. Ez is the source and V1 is the response, and replace delta delta z by ik, and this equation then gives you velocity which is equal to Ez over m I omega minus kz rather kz V0 into gamma 0 cube. This V1 is the z component of electron velocity due to the electromagnetic wave. Go over to the equation of continuity, which reads as delta n by delta t plus divergence of n v is equal to 0. Because this v is in the z direction, all velocities are in z direction, only delta delta z will be will survive here. Then linearize this term, so you will get delta n1 by delta t plus delta delta z of n0 v1 plus n1 v0. Linearization here means I have ignored the product of n1 v1. I substituted n equal to n0 plus n1, v equal to v0 plus v1, and ignore the products of n1 v1, and n0 v0 term does not contribute because it is uniform. So when you operate by this dial operator, that will vanish. So this is the equation. Now replace this by minus I omega delta delta z by ik, and you will get n1 is equal to n0 kz v1 upon omega minus kz v0. If you use the value of v1 that we had obtained earlier, this becomes n0 e kz ez upon m I gamma 0 cube and omega minus kz v0. This is a square. Density perturbation becomes very large in the vicinity when omega upon kz becomes equal to v0, when the phase velocity of the wave in z direction becomes equal to beam velocity. This is an important point here, and obviously it decreases with increasing gamma 0. So if you are having a beam of larger and larger energy, larger kinetic energy, then gamma 0 will be larger and this effect will be suppressed. Well, for generating electromagnetic waves you require a current. So current is at frequency omega is equal to minus n, the electron density in equilibrium, electron charge which is minus e, into velocity v1. But there is another term which is minus n1 e v0. Actually it is a product of electron charge and electron density into electron velocity. Electron density is n0 plus n1, electron velocity is v0 plus v1. So multiply these. n0 v0 term I have not written because that is a DC term, so that will not produce any wave. It is only terms that have a time dependence at the frequency of radiation that you want to excite or amplify has to be retained. So once you calculate this, substitute the value of V1 and V0 or N1, it turns out to be equal to minus N0 E square omega Ez upon m I omega minus kz V0 cube V0 square into gamma 0 cube, and that is in the z direction. So a beam, when travels in the presence of a low amplitude electromagnetic wave in a waveguide, it acquires a oscillatory current density, and this oscillatory current density will then give rise to the amplification of radiation. Now let us see how does it happen. The wave equation for the electromagnetic wave in the waveguide can be deduced from these two Maxwell's equations. Curl of E is equal to minus delta B by delta T, which is equal to I omega mu 0 H, and curl of H, which is equal to J plus delta D by delta T. Now dielectric is loaded in the waveguide, so D I can write, this term I can write down as minus I omega for delta delta T, and D is equal to epsilon 0 into epsilon R into E. This is the relative permittivity of the medium filled inside the waveguide, called dielectric constant, plus J, the current density which is given here. These two equations can be combined into one if I take curl of the first equation, and the result is curl of E is equal to I omega mu 0 curl of H. Use the value of curl of H from the second equation, it becomes omega square by C square epsilon R into E, and plus I omega mu 0 into J. This can be expanded as gradient of divergence of E minus del square of E. If I take divergence of E, this is an inconvenient term. So in order to obtain the value of divergence of E, take del dot of this equation. Then these two terms exactly cancel each other, and this gives me divergence of E turns out to be equal to, here this is minus I omega mu 0 into divergence of J. Because I am taking del dot, so del dot of E and del dot of J, omega mu 0 I have written upon this quantity omega square by C square. If I put C square as I think this is yeah, C square is, sorry, C square will go up, though not here, I am sorry, I made a mistake, C square goes up. So this can be simplified because c square is 1 upon mu 0 epsilon 0. So it becomes minus I upon omega epsilon 0, and j is in the z direction, so only delta delta z, which is ikz into jz will come there. This is all. So once I have obtained the value of divergence of E, my equation becomes simple, and I can write this equation as del square of E plus omega square by c square epsilon r into E is equal to, I can write that equation on the right as minus I omega by c square epsilon 0 into j, and then there is a term that I have brought from left, which is plus gradient of divergence of E. Divergence of E is minus I omega epsilon 0 ikz into jz. My goal is to write the equation for Ez. So z component of this equation I will write. This gives me, and del square is, I will expand it. So d2 dr square of Ez plus 1 upon r delta Ez by delta r plus d2 dz square of Ez. This is the value of this quantity. If I presume that there is no phi dependence, there is no azimuthal dependence of Ez. So this is the z component of this term plus omega square by c square epsilon r into Ez. The right hand side is minus I omega upon c square epsilon 0 jz. How about this term? Del operator z component is delta delta z, which is ikz. So if I put ikz here, then what do I get here? Ikz and minus I will become plus. So it becomes plus I kz square over omega epsilon 0 into jz. These two terms can be combined. I think I made a, I think I made an error. When I wrote down the expression for divergence of E, from here I forgot to write epsilon r here. Put epsilon r there. This epsilon r I missed. So if I take correct for it, then there will be epsilon r there and there will be epsilon r here. So these terms can be combined, and this d2 dz square I can write down as minus kz square. So this equation becomes rather simple, and let me write down the value of this, rewrite this equation. It becomes d2 Ez by delta r square plus 1 upon r delta Ez by delta r plus omega square by c square epsilon r minus kz square into Ez. This is equal to, if I take minus I omega upon c square epsilon 0 common and jz also common, here you will get a term which is 1 minus kz square c square upon omega square epsilon r. This is a similar factor as the factor over here. If I take this factor common, this is the same factor, and jz already I have obtained. When you substitute for jz in terms of Ez, this equation takes the following form: d2 Ez by delta r square plus 1 upon r delta Ez by delta r plus some quantity, a constant quantity which I call as k perp square Ez equal to 0, where k perp square is an important quantity that depends on frequency. It is a combination of this term and terms coming because of these, and its value turns out to be this much. Let me write down the value of this expression. It is a simple expression. K perp square turns out to be a common factor like this, which I can write as omega square by c square epsilon r minus kz square multiplied by 1 minus omega pb square beam plasma frequency square upon epsilon r upon gamma 0 cube omega minus kz v0 square. This is something like 1 minus omega p square by omega square kind of thing. If beam velocity is not there, beam is non-relativistic, and epsilon r is unity. So this looks like a plasma permittivity, and this is, if plasma is not there, then this is simple k perp in a dielectric loaded waveguide. So plasma contribution is contained in the second, or the beam contribution is contained in the second term, and through this we have to see how the beam transfers its energy to the wave, how the wave is amplified. Let us see. So I have to solve this equation with proper boundary condition. Ez is the axial component of electric field. At r equal to a, the wall of the waveguide, it must vanish, because if it is a metallic waveguide, then the tangential component of electric field must vanish. But before I do that, what is the solution of this equation? This equation is Bessel equation, whose solution is J0, Bessel function of 0th order. So I can write down the solution of this equation as Ez is equal to some constant into Bessel function of 0th order and argument k perp r, and the dependence of this field on time is like this, omega t, and its z is kz, z. So this is my field, and this must vanish at plasma boundary, or at the boundary of the waveguide. At r is equal to a, I want Ez to be 0, means J0 of k perp a must be 0. But if you plot J0 as a function of its argument, it goes like this. Suppose I plot here J0, if I plot of some argument x as a function of x, it goes like this. Means it is 0 at many values of x. This is called the first 0 of x, the second 0 of x, third 0 of x. Means J0 is 0 when x is equal to some values, they are called x0 n. This is called x01, this is called x02, this is called x03, and so on. The value of x01 is around 3. So what you get from here, if this is to be 0, then k perp a cannot take arbitrary values, it can take values only equal to this much. So k perp a has to be equal to the 0 of the Bessel function. Once k perp is quantized by this condition, then if I substitute the value of k perp in the definition of k perp, I get the dispersion relation for the electromagnetic mode. This is what we were looking for. So what you get is this put this value of k perp in that expression, and that becomes omega square upon c square epsilon r minus kz square. I am putting the value of k perp square multiplied by 1 minus omega pb square divided by epsilon r divided by gamma 0 cube into omega minus kz v0 whole square is equal to x0 n square upon k per upon a square. So this is the dispersion relation. This is a fourth order equation on omega, and this will give you 4 roots in general, and I am looking for the unstable root. Please understand, if the beam were not there, this term will be 0. So what I want to do, if the beam density is very low, I expect that the modification caused in the dispersion relation by the beam to be small. So I would like to take the beam term on the right hand side and non-beam terms on the left hand side. Then this equation becomes, so retain this into 1 and bring this on the left hand side. Then this can be written in the following form: omega square by c square epsilon r minus kz square minus x0 n square by a square, and then take this omega pb term on the right hand side, which becomes omega pb square upon epsilon r into gamma 0 cube into this resonant denominator kz v0 square multiplied by this factor, which is omega square by c square epsilon r minus kz square. This expression or this equation is very similar to the one that we encountered in two-stream instability of a plasma wave. What you can do, you may note that these terms are constants, only omega square is in the first term. So if I take epsilon r by c square common and divide that by this equation by that factor, then this equation can be cast into a similar form, and the form is like this: omega square minus, I will call this omega r square rather than omega p, this quantity I will write, and this can be put in this form: minus kz v0 square is equal to right hand side, I will call this as r. What is omega r square? Omega r square I am defining as a term which is equal to kz square plus x0 n square by a square multiplied by c square upon epsilon r, because this is the factor I had taken common. So this thing, and r turns out to be equal to omega pb square upon epsilon r square gamma 0 cube c square here multiplied by omega square by c square epsilon r minus kz square divided by, well, this is all. So this is the kind of expression, this equation we get, which is very similar to the true stream instability problem, and you expect that right hand side, though very small because the beam density is small, so this is a small term, but it can significantly modify the electromagnetic wave if these two factors are 0 simultaneously. So we solve this equation for a special value of k, kz, when kz v0 is exactly equal to omega r. So we say that because of this r, or because of the beam, when beam term is retained, the value of omega is modified, otherwise if it is not there, omega equal to omega r or omega equal to kzv0. But when this r is finite, omega is not exactly equal to omega r, we say that omega is equal to omega r plus delta, which is also the same thing as kzv0 plus delta, because I am choosing omega r is equal to kzv0. I am solving this equation so that if this term is not there, they are simultaneously 0, because I am expecting the largest growth rate as in two stream instability when this term is equal to this, omega r is equal to this factor. So in this limit I will solve this equation. Now I am again assuming that this modification is small as compared to omega r or kzv0. As a result, when I substitute this here in this first term, delta square I ignore, and when I put this in this term, this becomes simply delta square. So I get a delta cube term here. How about the right hand side? In the right hand side I will say that, well, put the value of omega equal to simply omega r, forget this delta term here, then this term factor becomes quite simple. If you just put the value of omega r from here, it becomes simply this whole factor becomes equal to, let me just write the value of this factor. This factor simplifies to equal to x0 n square by a square, simple, this factor, just substitute it. So I will use this expression, replace this expression by this term, and then r becomes quite simple, and just put this in there. My equation turns out to be like this. I get delta cube is equal to r divided by twice omega r. I multiply this quantity by exponential I twice L pi, because this is always unity. L is an integer, 0, 1, 2, 3, they are the values. So take the cube root of this equation, and delta is the similar expression as r upon twice omega r as 1/3 power into cos twice L pi by 3 plus I sin twice L pi upon 3. For L equal to 1, this gives unstable root, and the value turns out to be equal to r upon twice omega subscript r to the power 1/3. This is minus half plus root 3 upon 2. So the growth rate is gamma, which is the imaginary part of delta. So let me explicit after substituting the value of omega r and r, let us see how delta looks. The delta turns out to be this expression. Let me just write this. The growth rate turns out to be omega pb square c square x 0 n square upon a square, a is the waveguide radius, upon gamma 0 cube epsilon r square into 2 omega r or omega, same thing. This is the operating frequency of the Cerenkov FEL, 1/3 root 3 by 2. So the growth rate scales as 1/3 power of beam density. It scales as 1 upon gamma 0. With beam energy it falls down. How was the frequency? This scales as omega to the power minus 1/3. Higher the frequency, smaller the growth rate. But who decides the frequency? That is the important issue. The frequency of the wave is decided by this resonance condition, that omega r, which was is equal to, I had written the value of omega r, and let me just recall this value, which is kz square plus x0 n square upon a square c square by epsilon r has to be equal to kz v0. So, from this equation you can obtain the value of kz and put that value of kz multiply by v0, you get the frequency of the operation. So, operation frequency of the Cerenkov device, Cerenkov FEL, is this much. And as I mentioned, in the case of true stream instability, the instability saturates by particle trapping. I did not prove it there, but one can easily show that the same condition is equivalent, roughly equivalent, not exactly equivalent, to saying that when the electron beam transfers its energy. So, electron beam loses energy and its velocity falls down from v0b to, say, from initial value was v0 and final value is vf, which becomes equal to omega by k z of the wave, the growth will stop. So, as the electron beam loses energy, its velocity reduces from original velocity v0 to, say, final velocity equal to omega by kz, and in that case beyond this point it will not be able to generate the electromagnetic radiation, because the necessary condition for electron bunching in retarding phases was for electron bunching in retarding phases, retarding zones, you require v0 to be greater than omega by kz. So, what is happening? Initially the beam velocity is bigger than omega by kz. As the beam on an average lose energy and their velocity comes down to omega by kz, they stop giving energy to the wave. And if you calculate, so energy of the electrons, well, it is a little tricky dependence on v0 because a relativistic case. So, final energy minus initial energy of the electron divided by the initial electron energy, this is the efficiency of the device. So much fraction of electron energy will go to the wave, and this quantity depends on the growth rate. Typically I would say this is of the order of growth rate upon omega, the frequency of radiation, and this could be of the order of a few percent. So, Cherenkov free electron laser can produce radiation with a reasonable efficiency. You can improve the efficiency by forcibly slowing down the wave. You know what we have done in the waveguide, you have a lining like this, there was a dielectric here. If you taper the waveguide so that when the wave travels, it becomes slower and slower. So, what will happen? As the beam slows down, if you slow down the wave also, so that wave velocity is always bigger than the electromagnetic wave velocity, then the beam will continue to transfer its energy to the wave and the wave will be amplified. So, this by tapering you can increase the efficiency of the device. Tapering is a very important scheme of increasing the efficiency of the device. When we discuss free electron laser, we shall return to this issue of tapering and efficiency enhancement in some detail. Thank you very much.